Thanks very much, Jerry. In actual fact, this isn't going to be a really technical thing. It's more about concepts and ways of thinking. It's to do with things that I've become very passionate about in terms of developing the understanding of a more holistic way of ore body knowledge, which I certainly believe geometallurgy is a very big part of it. And maybe it will just give us some insights into how it can be better applied to the battery minerals sector in order to take advantage of the current desire for them. So I think many of you would have seen this statement coming out from the US at the start of the month. It was the Managing Director of Benchmark Mineral Intelligence. He was asked to report to the US Senate on the state of the battery minerals, lithium, cobalt, nickel and graphite. It was largely to sort of do a please explain, I think, as to why the US were underperforming. But I think it was quite startling, the results of it. And it does give an indication as to the seriousness of perhaps the way forward with battery minerals, in that there is going to be an incredible increase in demand and therefore the corresponding increase in pressure on finding supply. The graph that was presented there clearly tells it that if everything goes to plan, with all these mega factories are going to be built to cater for the supply of battery minerals, that there's going to be no shortage of consumers. I think some of those figures are quite startling, but the one that really sort of struck me was the 19 times increase in the demand for nickel, particularly as I've worked a lot with nickel, particularly in the laterite environment, and how we can actually take advantage of that and get a bit more confidence in the way that we handle nickel laterites, particularly in Australia and even more particularly in Western Australia. So, you know, I think everybody knows here that we do have incredible resources of battery minerals, and of all four of them, and a lot of them do exist in Western Australia. You know, we've got Greenbushes, which is a major force for spodumene, and that's considered the Rolls-Royce of lithium minerals. With cobalt, the bulk of the projects at the moment is coming out of Africa, in particular the DRC, but there are risks with that supply, and consumers are starting to look elsewhere for alternatives. In Australia currently, largely cobalt's being supplied as a associated product of mining nickel laterites, and that at the moment is currently dependent upon how fast we can mine the nickel. Graphite, at the moment, we heard a talk by Tony Cooper this morning on the Springdale graphite. China and Africa are currently the big players, but there's opportunities there, particularly in Western Australia, for enhancing the graphite resources. And nickel, I'll talk a bit more about nickel laterites later in the terms of the GEOmet space, but at the moment Australia has the largest economic reserves of nickel. Mostly 70% of our production comes from nickel sulfides, but 70% of our reserves exist in the nickel laterite space. So the question is, why would we not want to investigate producing more nickel from the nickel laterite space, despite the fact that historically there has been a bit of a history with lack of, or not so much lack of success, but difficulties in getting them going. I tried to find a really good sort of description as to what geometallurgy is. I looked at Wiki, and that gave a really boring talk on that, or a description of that. So I went around and asked a whole heap of people from various disciplines as to what they felt geometallurgy was to them. And totally different answers from everybody, depending on whether you were corporate or if you're an exploration geologist, if you're a mining geologist, if you're a process engineer. It was quite interesting that every one of them basically talked about the idea of geometallurgy in an aspect that meant something to them. All of them were right, I felt, but the one that really resonated with me was something that a process engineer once said to me. And he said that if you manage the bad bits, the good bits tend to look after themselves. And to my mind, and the work that I've done in geometallurgy and metallurgy and building ore control models that I'll talk about shortly, that actually hits the nail on the head. And the other thing that I have found it to be, that it's all about managing the physical properties of what you're dealing with. Now that's something that traditionally probably hasn't really been done until a much later stage in the project. This is one of my favourite slides. It's what I sort of talk like the circle of life. And it's basically the main stages of a project, which starts from exploration, goes through to resources and reserves, mine planning, mining and processing. Generally, I find that each of those disciplines operate largely in a silo, that everybody in exploration focuses on exploration. Resource geologist does his own thing. The mine planning engineer doesn't often come and talk to the resource geologist about what they're mining. And the processing, in my experience, it never comes to talk to the mining unless they've got something to complain about. So I've been working for a long time on the concept of an ore control model, which is where all the disciplines come together, providing the prize thing on which everything depends upon. And a large part of the success of the ore control model depends on metallurgy and geometallurgy. Now, historically, the metallurgical test work is usually done quite late once you've actually defined a resource. And it's normally done somewhere between resources, reserves, when you're trying to do a feasibility study. You usually do big samples, not a lot of them, and the results of that is basically given to the process engineers to design a plant based on, in my opinion, not a lot. A lot of the time it's been based on what's been gone before, and a lot of assumptions are made as to what's going on. Now, I certainly have first-hand experience of an operation where initially a plant was designed and it didn't suit the actual ore types in the deposit, but I'll go into that a little bit later. The pilot plant stage is also another stage that you get to after you've done your test work in the feasibility study, and again, that's even getting more and more large samples, and it's all relative, but what I've been finding is that there's been a lack of understanding of the actual detailed stuff that goes into making informed decisions as to what your ore feed is going to be. And the best place that I'm thinking that should be done is during the exploration phase. Now, when you think about it, when we're doing drilling and we're assaying and we spend millions of dollars estimating holes or the mineralisation in the ground to the nth degree, close-space drilling, blah, blah, blah. The fact of the matter is, as somebody who's done many resources, you usually find that the global resource doesn't change all that much from when you do wide-space drilling to when you do a close-space drilling. What does change is the level of detail. What does change is the increased understanding as to the variability of your grade. Nothing else. Just imagine what would happen if you took the plunge and decided to spend some of your exploration budget not on more close-space drilling, but actually trying to find out what the physical properties of the grade that the grade was sitting in. And that's going to be particularly applicable to battery minerals because these are unusual in that all the commodities are actually sitting in minerals. They're sitting in the lattices of your minerals. And we have to find a way of how we're going to liberate that, concentrate that, come out with a product at the end that's going to meet numerous markets with different specifications. I think it's way too late to be doing it at the metallurgical test work stage that's been traditionally the place where it starts. I think we would be much better off trying to get a handle on how much of it we can actually produce out of the ground at a much earlier stage. It's a risk assessment, it's risk mitigation, and it will give people the opportunity to decide whether or not they can actually walk away from the project. Battery metal ore bodies are extremely variable in grade, mineralogy, alteration and physical properties, and that's the fact, and that's the thing that we have to keep in our mind the whole time. The whole point is basically taking enough samples that we can actually demonstrate that and move forward so that when we do come to do our larger scale testing, we have a much better idea of the type of plant that we're going to need, and we can actually, and here's a novel thought, design a plant that actually suits the ore types in the ore body. The success for that is an informative ore control model, and all sorts of information can go into that. So the main point of this is that with our variability sampling at the exploration stage, the important point is to actually do it. Do more of it, because it has to have the same statistical robustness as we would trying to estimate our grade. And do it sooner rather than later so that you have a much better idea of what you're dealing with. You need to take enough samples so that there's a spatial distribution across the ore body. High and low grade samples need to be taken. You need to quantify your limits, and you need to make sure that you have sufficient waste characterisation of your ore. You need to have statistical robustness, and for goodness sake, do your multi-element geochem, because more often than not we find that there may be a critical element coming out of the product that we have absolutely no idea how that's going to affect the quality of the product. So for the last sort of 4 minutes that I've got here, I just wanted to talk about nickel and cobalt in the laterite space. As you can see, that the laterites are spread all around the world, as are the sulfides. As I mentioned before, 70% of the resources are in the moment in nickel laterites. This is a very well-known slide showing the profile of a nickel laterite. And the key thing about these things is that there are two main ore types, which is the limonite zone, and that's your iron oxide zone, and the saprolite zone, which is our magnesium silicate zone. And nickel can appear all throughout that. But the other key thing is within those two zones, there are several different material types that need to be managed, and it's the physical properties that's the driver. It's the physical properties that will tell you what the upgrade of the nickel is going to be, and if you don't understand that and don't have a handle of that, then when you start to process that, it's going to cause all sorts of troubles through the plant. Traditionally, the processes have been mostly smelting. That sort of deals with silicate ore. In Western Australia, we've certainly gone in some of the laterite operations that we've had, the acid leach or the HPAL circuit as well. But that has its limitations in that, particularly with HPAL, it really can only deal with limonite ore. The advantage with that is that it has high recovery. Traditionally, they haven't been successful in the early stages, and the thoughts are that perhaps it was because the plant wasn't designed properly, or the process wasn't good, or the beneficiation, if that was the case, wasn't the problem. I would suggest, and I know for a fact in a couple of them, that it was just as much because the plants had not been designed to deal with the entire gamut of the ore types that were sitting in the deposit. And if perhaps they'd taken time out to actually understand those, then they would have been able to build flexibilities into the plant to handle it, or else make the informed decision that they weren't going to mine it. These are profiles of typical nickel and cobalt laterites in WA. Murrin was a clay deposit, so you can see it's largely a sort of a smectite zone that they're mining. Ravensthorpe was an oxide deposit with probably equal amounts of limonite and saprolite. But the whole point that I want to show here is the variability of these profiles. Each nickel laterite deposit in the world is different. It has its own characteristics that have to be understood. And even though the principles behind it are the same, we can't go in with these types of deposits, or even any battery mineral deposit, assuming that one is going to be the same as the other. I think I just said that. These were just characteristics of the two operations, probably the biggest ones. Murrin is still operating at the moment. Ravensthorpe is in care and maintenance. The intention is to get it up and running when the nickel price goes. When that happens is anybody's guess. So moving back just for the last minute, I will skip that because it was just to show that the fact that putting GEOmet into the ore control model will basically make the ore control model what you do your mine planning on, because it will have your recovered metal. So to end, the way forward in thinking is to actually look forward, and that is to basically look ahead and see what the product specifications, what type of product you want to produce. Step back, take the time at your exploration stage to do the geometallurgical sampling, understand the physical properties of your ore just as much as the grade properties of the ore, because the two go hand in hand, they're not mutually exclusive. The last one is to think big, and this is probably a bit sort of controversial because we don't do it, but take an integrated approach, get information from every person in your organisation. If you don't have the people, go to the consultants, get the ideas from your exploration geologist, the resource geologist, the metallurgist. Have an idea at the start what your goal's going to be. Because at the end of the day, that exciting high-grade discovery of 1 billion tonnes isn't going to be able to get out of the ground if you can't process it. Thank you.